In this video, I'll talk about some important concepts regarding some power computation. For instance, harmonics, like when you have harmonics, how to calculate power factor and impedance and other things. These are very simple concepts, but unfortunately, sometimes there are errors in handling certain special cases that I will talk about, such as power factor. So first, let's start with a quick refresher. What is the root mean square, or RMS? So the RMS is the effective value of voltage or current, effective value of a periodic voltage. So if you have a periodic voltage, waveform is based on the average power supplied to a resistor. So if you have a DC voltage, so if you have DC and you connect it source, so you have a resistor, for instance, then you supply the DC to this resistor, so the resistor will consume this power here, which is VDC squared divided by R. So for a periodic voltage across a resistor, so if you apply a periodic voltage across a resistor, the effective value of this voltage will be as effective as the DC voltage in delivering the average power. In other words, it would be in this form here. So that P will be V effective squared divided by R. And we know how to calculate the average power when you have a periodic signal. It's so you can integrate over a period, 1 over T divided by P. 1 over T times integration from 0 to 1 period, T is period, times the instantaneous power. We know power is V times I in time domain. So if you carry out, we know I here, current is V divided by R, Ohm's law. So you end up with V squared, so 1 over T integration of V squared divided by R. R is just constant. So we wrote it in this form, which is basically what we are targeting, which is this form here. So basically the effective value, which is also root mean square, RMS, is the square root of 1 over T times integration from 0 to T times the square of voltage. And you integrate over with respect to time. So similarly, you can do the same thing for current. It's the same. So when you have sinusoidal signals, again, this is a special case. You only apply this if you have a sinusoidal. So in the form of, so V is equal to Vm magnitude peak, basically, which is root 2 times V RMS times sine of 2 pi ft. F is frequency, T is time, and I'm ignoring phase shift here. And we say sinusoidal because you can write this in terms of cosine, because we know cosine and sine, you can transfer from one to the other. So even if we say sinusoidal, sometimes we use cosine, which is fine, because you can transfer back and forth, however you want. So then the RMS value is just that peak value divided by root 2. But again, you only apply that if you have a sinusoidal signal. Power system equipment is rated rating is based on RMS. You will never people talk about peak, or sometimes the RMS subscript might be dropped. So someone will say 208 volt AC. Someone might ask, well, is that peak? Is it peak to peak? Or is it RMS? So peak to peak and peak do not apply. So it's implied it's RMS. Now, if we have a voltage VT, that's periodic. So this is one condition, which is the sum of periodic voltages that are orthogonal. So that's another condition. So if they are orthogonal, in other words, you have this VT is the sum of V1, V2, plus Vn, which are, all of them are periodic and orthogonal. In general form, if you take V1 times V2 is 0. That means that V1 and V2 are orthogonal. So two conditions, periodic and orthogonal. You can take V1 times V3, the same thing. So you do that for any two. Then if those two conditions are met, periodic, orthogonal, then I can, to calculate the RMS, I don't have to go through all this crazy integration, you know, that I showed here. You don't have to do that. That's the nice thing about a lot of concepts in electrical engineering. So then all I need to do is, if they have to meet those two conditions though, then you take the first voltage, RMS of it, you square it, plus the RMS voltage of the second voltage, square it, plus dot, dot, dot. You do it for all the voltages. Or if you want to write in summation, this is how you do it. You do the same thing applies to current. So here's a quick example. I have a voltage that's 5 plus 10 times cosine omega plus 15 times cosine omega t, 3 omega t. Now, we know cosine is periodic, so that's one check. We know cosine omega t times cosine 3 omega t, the two signals are orthogonal. In other words, they have different frequencies. I should have mentioned this here. So they have different frequencies. That's what we mean by orthogonal. Different frequencies, because one has omega, the other one has 3 omega, so two different frequencies. Because omega is 2 pi f. So 3 omega is 2 pi times 3f. So f, 3f, so different frequencies. So they're orthogonal. Then to calculate the RMS, all I need to do is take the DC part, which is 5 squared, plus 10 divided by root 2 quantity squared, plus 15 divided by root 2 quantity squared. Because you see 5 is just DC, I didn't divide by root 2. Why did I divide 10 by root 2 and 15 by root 2? Because 10, when you have cosine or sine, typically this value, this 10 here, volt, is peak. But I need RMS from this equation here. And we know if it's sinusoidal, we know to calculate, so Vm or V peak is 10 volts. So to calculate VRMS, it's 10 divided by root 2 if I apply this equation. So that's all I did here. So then I get 13.69 volts. Because if it was not for this nice equation here, I would have to apply this crazy equation here to calculate the RMS. You can imagine it's a lot of integration, but because those two conditions are met, I skipped all the integration and just applied this nice equation here. Now let's take the same voltage, except I changed the 15 cosine to have a frequency, the same frequency as the 10 cosine. In other words, so this is omega, this is omega. So cosine, it meets the periodic check. Let's check the orthogonal case. Well, omega, that means they have the same frequency. They don't have different frequencies. That means this does not check. Because remember, our sinusoidal with different frequencies. So in this case, they do not meet the orthogonal condition, so I cannot apply the previous equation. So since 10 cosine omega t and 15 cosine omega t have the same frequency, which is omega, we cannot use this equation here. If you use this equation, your result will be incorrect because the two cosines are not orthogonal. And just notice sometimes when people say frequency, you know, they might say omega, frequency, but we know omega is 2 pi f because omega and frequency are kind of directional, they're proportional. That's why people will use the two kind of interchangeably, like omega and f, you know. So now, then what should I do? I have to combine the two signals that have the same frequency first. So then, when you have a, so 10 cosine omega t plus 20 degrees. So this is time domain. If I want to convert it to frequency domain using Laplace transform, so this is peak, but when we do Laplace transform, typically we use RMS. So divide that by √2. Then we kind of put this symbol here to mean angle. So this just means angle. So then we take whatever phase shift we have, including the sign. So it's plus 20. I'm not going to use plus, or let's just use it for because if you had minus, then you have to use that minus. So then you do the same thing for the other one. So what I did, since 1 over square root 2 is kind of common to the 2, I just put it out and I put the brackets here, kind of factor it out basically. Then 10 with an angle, so the magnitude is 10 with an angle of 20. The other one is magnitude 15 with an angle of 30. Then if you carry out the calculation, so 1 over square root 2 times, so I get this with an angle. So you have to kind of plug this in MATLAB or calculator. So I get this equation here. Then I can go back to time domain because I combined, because I have these two signals with same frequency. Now I can combine them in as one signal. So I go back, v is equal 5 plus, again, I'm going to go back to cosine because I started with cosine. Because if you had sine first, you'd have to do some conversion. But anyway, because this value here, this is RMS, but when I multiply it by cosine, I have to convert it to peak, so I have to do times √2. So this √2 will go away. So plus this value here times cosine, because I started with this frequency, plus this angle here, 26. So now I combine them. Now I can go back and use this equation. So it's 5 squared plus 24.9087 divided by √2 squared. So I get 18.3091. So that's how you kind of handle. So if you have signals that are orthogonal, periodic, you can use this equation here if it's a voltage. If it's current, obviously you're going to use this. It's the same, you just replace V with I. If they have the same frequency, then you have to combine the signals with the same frequency before you can apply this equation. So apparent power, so if we're talking just magnitude, S is V RMS times RMS, and that's in VA, volt ampere, or kVA, MVA. Apparent power is what you use to specify equipment ratings. We don't use watts with some exceptions, but typically S is what gives you the total current. So general form for power factor, general form for S is P divided by power factor. Then power factor is P divided by S. We know S from this equation here is V RMS times I RMS. So this is kind of the general equation. So this equation here is general. We don't care if we have a linear system, it has harmonics. If you use this equation, you will be correct anytime. So for sinusoidal voltage and current, so sinusoidal, that means no harmonics. You don't have any nonlinear issues, basically. Then we use this equation here. Power factor is equal to cosine theta, where theta is the angle between voltage and current. I cannot emphasize this enough. This is a special case. Power factor equal cosine theta only if you have linear systems. If you have harmonics, you cannot. So And I have example. If you have harmonics, you cannot use this equation. So then you have to use the general formula, because why do we say power factor equal cosine theta? So again, if I go back here to this equation, the general formula, so P, it's equal to P. What is P? If I want to write it in general, so it's V1 times I1 times cosine theta 1 plus V2 times I2 cosine theta 2 plus dot dot dot. How many you have? So this is here fundamental frequency or harmonic order is 1. So if you have 60 hertz system, it's 1 times 60, which is just the fundamental frequency. This is second order harmonic. H is equal to 2. If you have 60 hertz frequency, then it's 2 times 60 is 120. So this signal would be at 120 hertz. We know VRMS. What is VRMS? From the previous equations, it's V1 RMS squared plus V2 RMS squared plus V RMS, V3 RMS squared, so on and so forth. You write them all out. Times RMS current. What is the RMS current? From the previous equations, it's I1 RMS squared plus I2 RMS squared plus dot dot dot, because if you have other harmonics like third, it's I3 RMS squared plus I4 RMS squared plus I5 RMS squared. So that's the general formula. Now, for sinusoidal voltage and current, that means I don't have any harmonics. That means this term is 0. That means the only term I have here is V1. V2, V3, V4, all of them are 0. The same thing with current. So what do I end up with? I end up with power factor is equal to V1 times I1 cosine theta 1 plus 0, which I'm not going to write. And the voltage is just V RMS, V1 RMS squared, because the other ones will be 0 times I1 RMS squared, which is V1 I1 cosine theta 1. What is this here? It's just V1 RMS times I1 RMS. V1 RMS, sorry, I dropped the RMS subscript, will cancel out. I1 will cancel out. So power factor cosine theta, or theta 1 in this case. So that's why it's a special case, only if you have no harmonics. If you have harmonics or nonlinear devices that cause harmonics, you cannot use this equation here. So very special case. So I already kind of went through for sinusoidal. So if now harmonics are there, power factor P divided by S, you don't have any harmonics, then it's just RMS voltage type, the fundamental basically. So this cancel out, kind of what I kind of went through, then you end up with cosine theta. So power electronic circuits typically have voltage and or currents that are periodic. They are periodic, but not sinusoidal, non-linear. So they produce harmonics, in other words. One common error is the attempt to apply some special relationships for sinusoids. And I kind of talked about one. Power factor equal cosine theta only if you have sinusoidal systems. That means no harmonics. It's a special case. So Fourier series can be used to describe non-sinusoidal periodic waveform series of sinusoids. The power relationship for these circuits can be expressed in terms of the components of the Fourier series. So what Fourier says is, a non-sinusoidal, if you have a non-sinusoidal waveform that meets certain conditions, can be described by Fourier series of sinusoid. The Fourier series, if you have a periodic function f, can be expressed in trig form as, so if you have a function, so some dc plus, you know, the sum of this mess here, so then you can, by what Fourier series says, you can write that function in these terms here, like some dc and this term here, this term. Again, the intent of this video is not to go over Fourier series, but basically if you have like some signals that are periodic, they meet certain conditions, you can write that signal in terms of like sinusoids basically. So superposition for power is not valid when the sources are of the same frequency. So P is equal to, or average power, the sum of all the powers at, you know, a different frequency. So you can also write it in terms of, so for n equals 0, we know P is equal to V0 times I0 times cosine, and if it's so basically it's DC, you know, so the n equals 0, we're assuming it's DC, then for DC we know the power is just V times I, plus then instead of starting from 0, I'm just starting from 1 because I already wrote the term for n equals 0 out. So then what you do, you sum up, and I kind of went over this in the previous slide. So the RMS voltage at term n times current, RMS current at term n times the cosine, and you take the difference of the phase angles, you know, between voltage current at that term n. And I kind of went through this when I did, you know, when I wrote down kind of these terms here, V and I. That's all I'm kind of summarizing here. So let's assume you have, so basically why do we need this? Well, if you have a circuit, for instance, hypothetically speaking, you have some DC in series with first order harmonic source, all the other terms that you have supplying a load. Now, and we'll apply like how to handle this situation, you know. So if you have a non-sinusoidal periodic voltage with a Fourier series of, you know, so voltage is 9 plus, I'm not going to go through all this. Basically, you have this voltage here. It has a bunch of terms. So you have some DC, then you have 2 pi times 60. So 60 is the frequency. So H equal 1. This one, H is equal 2. H equal 5. H is equal to 7. So you have first order harmonic, which is just fundamental. You have the second, the fifth, and the seventh. So how do we handle this? Like if we have so you have this voltage here, source that has some harmonics along with DC, then it's supplying this load that's a 9 ohm in series with an inductor of 20 millihenry. Again, this is an application of what I showed here. So we want to determine what is the power absorbed by the load. We know the only thing that's going to absorb power is the resistance, the 9 ohm reading. So we'll use superposition, because the reason being is because they have different frequencies. This one is 60, this one is 120, this one is 5 times 60, 300, this one is 7 times 60, 420. So different frequencies, we can use this equation. So the voltage at n equals 0, or DC, is just 9 volts. I don't have to do anything. V1 at H equal 1 basically. So it's this term here, because this is a peak, but we need the RMS. So I need to divide that by root 2. So that's what I'm doing here. And the angle is negative 12. So that's what I wrote here. So 10, basically 10 volts with an angle of negative 12. So V2 is 25 root 2. So root 2 will cancel out with an angle of 11. So 25 is the magnitude with an angle of 11. So V5 is 35 times root 2. So root 2 will cancel out. So I get magnitude of 35 with an angle of 9 degrees. 7 is 31 times root 2. So root 2 will cancel out. So 31 magnitude with an angle of negative 19. So those are the RMS voltages. Now if I want current, I have to do Ohm's law. So for n equals 0, I0 is just V0 divided by R, because we know impedance in general is R plus J X, which is R plus J 2 pi F L. Because I have an inductance in this case for n equals 0, which is the DC, basically F is equal to 0. So this term will go out, will go away. So that's why I divided by R only here. So V is 9, the resistance is 9 ohms, so I get 1 amp. Now, kind of what I was saying, probably I should have started with this. IN, like any term basically, any term N is V at that term, or the voltage Vn divided by R plus J N times omega 1 times L. Omega 1 basically is just a frequency. In this case it's 60 because it's not going to change, because if you go back here, all of them here are multiplied by 60. That's all I'm saying here. Sorry, I should be specific. Omega 1 is 2 pi F1, and F1 is 60 hertz, basically. So this is kind of the general formula. And the impedance depends on frequency, because reactance depends on frequency. So the omega impedance is R plus J. R does not depend on frequency in this case, plus J times 2 pi F times N times L. N means whatever harmonic order I have. So now I will apply this formula. I1 is V1 divided by R plus J omega 1. So if I go through, I already calculated V1 here. So I'm just plugging the numbers, 9 plus J, 2 pi 60 times the 1, which is, because I'm doing N equal 1, times L, because just remember 20 millihenry, so I convert that to Henry, which is 20 divided by 1,000 basically, which is 0.02 Henry. So I get this value here. So I do the same thing for, sorry, I get this value here. I do the same thing for I2. So basically it's just direct application of the formula. So I calculated all the currents. So kind of summary, I0 is 1 amp, I1 is this value here, I2, I5, I7. I know load current, I have to go back kind of to, if I go back to time domain, it's I0 plus I1 root 2 times, because again, you take I1, which is the RMS, you multiply by root 2 to get the peak, times cosine, because again, I'm doing, you know, kind of like I1 in time domain is V1 in time domain divided by the impedance. Then, because if I started from voltage, voltage has this here. So that's why I kept it. Plus the angle of the current, I1. So if you go back here, I1 has this angle here. That's what I mean by this term here. So you do the same thing for all the other terms. Basically, I'm converting from RMS to time domain using Laplace transform. So with this kind of symbol here, just means the angle of I1. So then if I plug the numbers, I get this crazy equation here. Now, power at each frequency is the Fourier series, in the Fourier series determined by. So for the DC term, P0 is just V0 times I0. Now, at omega equal 2 pi 60, or n equal 1, basically, so P1 is V1 times I1 times cosine of the angle of voltage minus angle of current at n equal 1. And I already calculated them. So if I carry out the calculation, I get P1 is equal to 6.53 watts. This is n equal 2. So 2 times 2 pi 60. So if I carry out, I do the same thing. This is n equal 5, n equals 7. So then I can use superposition. Why? Because the frequencies are not the same. If the frequencies were, if two signals had the same frequency, I would have to combine them first. But since they have different frequencies, I can use superposition. So the total power consumed by the resistance is the sum of the individual powers at each frequency, basically. That's what I'm doing here. So I sum them up, I get 44.13 watts. Again, caution here. You can only apply this formula if the signals have different frequencies. This is superposition, basically. If two signals had the same frequency, like I said, you have to combine those signals first, then kind of go through. So I calculated 44.13. Alternatively, you don't have to go through all that calculation. You can just say P is the RMS current times the resistance. Again, I can take advantage of periodic from previous slides, orthogonal. So superposition, orthogonal, they're kind of the same thing, you know. So periodic, check, orthogonal, check. All I need to do to calculate the current is use this equation from the previous slides. So the RMS current is the DC current squared plus I1 squared RMS. Again, I dropped the subscript, but this is RMS. Sorry, this is DC, so it doesn't matter. RMS, RMS, RMS. So then if I go through, I get the current is 2.2142 amps. So if I square that times 9, I get the same result, basically. So again, that's how you kind of calculate the power consumed by the resistor when you have a nonlinear system. Thank you and have a great day.